finish this section, I'd like to talk about lateral surface area. Lateral means around the sides, and in the most simple situation that we can think of, we'll have the usual kind of setup. I'll have some graph of some function, say y equal f of x. I'm going to revolve that around the x-axis, starting at x equal a, ending at x equal b, and generate some three-dimensional solid shape. In this case, though, I'm not interested in the volume of that. I want to know how much area is generated around the sides of it. By the sides, I mean I don't include the circle at the left end or at the right end, just the lateral part, the side part. In order to get anywhere on this, we need a fact from geometry. Now imagine I have a shape that looks like a right circular cone with the top cut off of it. At the base, I'll have a big radius. At the other end, I'll have a small radius, and the number L is the distance along the side. So not the horizontal distance or the vertical distance, but what they call the slant distance, the distance along this path. In geometry, it's shown that the area of such a thing is 2 pi times the radius times the length along the path. And by radius, I mean some number that's between the big radius and the small radius. We could state exactly what that number is, but as it turns out, it isn't going to be important to us. As usual, we'll divide the range of x values up into smaller pieces. We'll think about what happens with each one of these pieces. If, for instance, I take this one, that one, and revolve it around the x-axis, I get a shape that strongly resembles a frustum. The big radius is going to be the y-coordinate at this end. The small radius is the y-coordinate at this end. Because I'm revolving about the x-axis here, the length along the side, which we've been calling L on the previous page, is going to be the length of the graph that goes with this one piece. It's going to be the arc length that goes with this one piece. In the simplest of all possible situations, our recipe is just going to be this. If we knew how to get the chunk of arc length, we would be in business, but that's what we talked about in the first part of this discussion. The amount of surface area that goes with the frustum that comes from revolving that one strip about the x-axis is 2 pi times the radius times the slant length, as it's also known. In this case, that will be 2 pi times f at ci times the amount of arc length is approximately radical 1 plus the square of f prime evaluated at ci times delta xi. And at this stage, everyone knows what's going to happen. We add up all the contributions, and then to make our approximation perfect, we take the limit as all of the sub-chunks shrink down to points, as all of the delta xi's tend to 0. Obviously, this is the definition of an integral. Having said our recipe about 1,000,000 times, I will not say it this time. This is how we calculate lateral surface area when we revolve y equal f of x about the x-axis. As a simple example, let's look at the graph of y equal x starting at x equals 0, ending at x equal 1. We'll revolve this graph about the x-axis. I want to calculate the lateral surface area. Since the derivative of f is a constant at 1, The quantity underneath the radical sign is particularly nice. It's 1 plus 1 squared. I'm going to have a factor of square root of 2. Also, I have a constant factor of 2 pi. By this point, it should be clear that the integral from 0 to 1 of x with respect to x is 1 half x squared evaluated between 1 and 0, 1 half times 1 squared minus 1 half times 0 squared is 1 half. This will cancel the factor of 2 in the 2 pi radical 2, leaving pi times radical 2 behind. This is the surface area of this cone, not including the area of the circle at the right side. If a is a positive constant, then the graph of x squared plus y squared equals a squared is a circle of radius a centered at the origin. If you solve for y in terms of x, it could be that y is the principal square root of a squared minus x squared, or the negative of that quantity. If you use the first one, since the principal square root's never negative, what we get is the top half of the circle. I'm going to revolve this around the x-axis and find out what the surface area of a sphere of radius a is. The radius of one of the rectangles is going to be the y-coordinate, the function value, radical a squared minus x squared. In the rest of it, I have to square the derivative of y. I have to add 1 to that. I have to do the square root of that, put the result in as a factor in my integral, and integrate with respect to x. At first glance, this is not very promising looking because it's very complicated, apparently. Let's simplify the quantity underneath that second square root symbol to start with. Since this just involves algebra and calculus 1, I put in the steps here and omitted all the talking. That second square root quantity, in the end, works out to be a divided by the square root of a squared minus x squared. By itself, this is not looking good at all until we put it back together with everything else. At first glance, this doesn't look very good, but then a miracle happens. The square root of a squared minus x squared cancels out on the top and bottom, leaving only the a behind. A is a constant. The antiderivative of a constant with respect to x is the constant times x. I have to evaluate the antiderivative when x is equal to a and when x is equal to negative a. I'll have to look at a times a minus a multiplied by negative a. I'll have a squared minus the negative of a squared. A squared plus a squared is 2a squared. Multiply that by 2 pi, and you get the formula for the surface area of a sphere of radius a as 4 pi a squared, which, if you look it up in geometry books, is the correct answer. I just wanted to do a couple of examples, a couple very concrete, and then a slightly more abstract one like this. As you can see, these ideas actually do produce the correct results. Next, we'll start talking about work, as in energy. Until then, I hope everyone's having a good day. I'll talk to you again soon.